goes with the story of NUMECA. Back in the 90s, NUMECA was just a few people working on the software, and today, 15 years later, we have a software which is now known and respected by the worldwide turbomachinery community.
From meshing to results visualization, Fine Turbo is a complete toolset for turbomachinery flow analysis.
And this is Fine Turbo. So that's a tool, it's a CFD tool which is very dedicated to turbomachinery. And we believe that a general purpose software will never really be able to compete with a tool which is dedicated. Meshing is a key for a successful CFD process. So we need high quality meshes, that's important in order to trust our solutions. And we also expect those meshes to be generated automatically. And this is what you get with AutoClean, which generates those meshes in all types of turbomachinery components in a few minutes.
In addition to the amazing multi-stage meshing capabilities of AutoGrid 5, automated structured meshing is pushed to new levels, allowing users to add complex details such as partial gaps, full fillet capture with butterfly topology, cooling and CHT meshing, non-axisymmetric end wall treatments, and more.
An important module of the Fine Turbo solver, which generated a lot of interest over the last 5 years, is the Nonlinear Harmonics. So this is a technique that allows calculating unsteady flows in turbomachinery and rotor-stator interactions at totally affordable CPU cost.
NUMECA integrated the pioneering nonlinear harmonic method into Fine Turbo.
So this is an example of a multi-stage axial compressor where the NLH is used not only to model rotor-stator interactions, but also rotor-rotor and stator-stator. So this case is a supersonic axial turbine, which we resolve in a few hours on 12 cores. So this is a validation exercise we have done on basis of a turbocharger turbine stage. And we have compared the NLH results to a full unsteady 360 degrees analysis. And we can see we have a very close match, including the shock structure. So here we see an example of a compressor optimization, where the NLH has been used in order to attenuate the unsteadiness in the pressure field. So the next slides show the application of NLH to open rotor. So this is an application where the gap between NLH and the standard unsteady analysis is very large because of the very small time scales that are needed in a standard analysis. So NLH can also be used to model the interaction between a fan and a nacelle and the ground and get the unsteady pressure signal. All have tight schedules so the amount of analysis we can perform within a certain time frame is very important. The solver speed aspect is something on which we always insisted a lot in Fine Turbo, and the tool is now extremely competitive on that aspect.
This includes fully transparent procedures to partition multi-block structured grids so that they may be easily distributed across thousands of cores while maintaining an optimal load balance. This is an example of a massive HPC scale problem. The model includes two conical bodies exposed to a Mach 4 stream adjacent to a flat plate. The objective of the study is to resolve the shockwave boundary layer interaction. The flow model has been meshed with up to 4 billion cells and solved on thousands of cores using the Jaguar Cray XK6 supercomputer at the Oak Ridge National Lab. Another interesting study, the unsteady solution of a transonic fan stage. The mesh size is 350 million cells. Solving nonlinear harmonic at 6 frequencies makes this problem truly challenging in the HPC scale in terms of memory management. Performance numbers show near linear parallel scalability distributed on more than 4,000 cores. Besides HPC performance, It is also important to minimize computing time for any given number of cores and to extend the benefit of our solver speed to all users. NUMECA is developing the most advanced convergence acceleration techniques and materializing our efforts with Fine Turbo's CPU booster. This 1.5 stage transonic compressor is a perfect example of the benefits of CPU booster. With a mesh size of 6.5 million cells, distributed on 3 processes, at standard solver speed, convergence is reached after nearly 8 hours. With CPU booster, convergence is reached in only 2.5 hours. An additional interesting example is a cooled 2-stage axial turbine. With a grid size of 2.2 million cells, this model may be solved in only 40 minutes in serial mode with CPU booster.
So something that's very enjoyable for the NUMECA staff is to receive feedback. And usually what we hear is that the people who start using Fine Turbo, from meshing to solving, post-processing, feel that this software has been developed by people who were understanding the needs of a turbo machinery designer, or could even anticipate those needs. We see more and more people, small, large companies, joining the Fine Turbo community.